We're still working on section 22.3, the Aldol reactions. And in yesterday's material, we looked at the Aldol addition, we looked at Aldol condensation, and we also looked at the crossed Aldol reaction. And we were working on the worksheet showing how the crossed Aldol reaction can produce up to 4 different products, not including stereoisomers, which, as you can imagine, is a bit of a nightmare in terms of yield. Like, what if we only wanted product 2 and we were going to make all these other products along the way, and that just decreases the yield of our desired product. So, of course, we have a workaround in this situation, and this is called the directed Aldol reaction. So directed Aldol reaction is a type of a crossed Aldol reaction. It is between 2 different aldehydes. But we try to have better control of it. We don't just throw everything together and let it all mingle. In the directed Aldol reaction, one product is attempted to be forced over the others. So we are trying to make just one product. And the way that we go about doing this is by trying to minimize who can attack who. So the way that we do this is we start by reacting only one, either A or B, react one of our aldehydes, one type of aldehyde, with a very strong base, LDA, very strong base. Which you have met LDA before, not that long ago. It is lithium diisopropyl amide. That's a lone pair. It looks just like a line, but that's supposed to be a lone pair. So this is LDA, super strong base. And when you react an aldehyde with LDA, ideally you're going to get 100% conversion, no equilibrium, 100% conversion of that aldehyde to the enolate. So enolate. So let's say that we're reacting aldehyde A with LDA. We're doing aldehyde A with LDA. So that means that aldehyde A is going to turn into the enolate, and aldehyde A is going to be able to attack. But all of aldehyde A has turned into an enolate. So this reaction where A attacks A is no longer an option anymore, because all the A molecules are going to be attacking and no longer attackable. So we've just completely eliminated that possible reaction. Also, all of the A's will be attacking, not attackable. So we've eliminated that reaction as well. So already we've got it narrowed down to just 2 reactions. So once we get all of our aldehyde A converted to the enolate, then we are going to add the second aldehyde to the enolate. And the hope is that since aldehyde A is enolated, that's not a real word, but it's all in the enolate form and it's ready to roll, it's ready to react. The hope is that A is just going to get really busy attacking B, and that's all that's going to happen. And the B molecules are not going to be able to have the time to convert themselves to an enolate and attack each other. So this reaction is just becoming very unlikely. So that is how, in theory, that's how this is supposed to work. And it actually works pretty well. Let's go to our worksheet. We're still on this 22.3 worksheet. And what we're going to do on this worksheet is kind of like a retrosynthesis thing. So we're going backwards here. We are looking at how we could make these compounds through a directed aldol reaction. So we have to retrosynthesize. What aldehyde and what aldehyde do we need to mix together to get this particular product? Retrosynthesis, reverse aldol reactions, they actually can be pretty hard. And so what I'm going to do is just kind of give you some tips on how I think it's easiest to approach these reactions. So when you're starting with the alpha beta unsaturated, this guy right here, it is actually, in my opinion, it's easier to approach the synthesis. I wonder if this can... Oh yeah. Approach the synthesis like, first let's pretend, what did this look like before we did the dehydration reaction? So prior to dehydration, there was an OH here and there was a hydrogen here. And that's what we removed to get to that unsaturated compound. So I feel like it's easier if we imagine it in this form, like that. And then what I want to do next is I'm just kind of backing up. Prior to us having this aldol, we had an O- right here. So that was the second to the last step. And prior to that, prior to having that O-, we actually had a carbon-oxygen double bond right there. And that carbon-oxygen double bond was disrupted when we made this bond right here. So that bond that I just squiggled, that was the bond that was made when these two guys reacted. So let me just kind of undo all of what I did right there. And we're just going to really back it up. So what I want you to do is first return the molecule back to the aldol. So put that OH group back on. Make sure that it's going onto the beta carbon, not the alpha carbon, but the beta carbon. And then I want you to back it up to the O-. So before you protonated. And then I want you to put that carbon-oxygen double bond back. And when you put that carbon-oxygen double bond back, you're going to have to break a bond. You're going to have to either break this bond right here, or you're going to have to break this bond right here. So you got to think about, which bond am I needing to break? Well, you know that this reaction involves two carbonyl compounds together, like two aldehydes or two ketones. So let's think logically about this. If we did it this way, if we broke the bond like this, we would end up with this molecule right here. That's not how we start aldol reactions. We don't start with a dialdehyde, that's what this is. We start with two different aldehyde molecules, so that's not going to work. This little guy right here, that's not the bond that we want to break. We want to break this one. We're always breaking bonds towards the other carbonyl group. So that gives us this enolate and this aldehyde right there. So we're almost done. This is one of our reactants right here. So we've got that part of it figured out. And then the other question is, how do we get this particular enolate? This enolate is made by reacting LDA with that aldehyde. So here's our other aldehyde. There we go. I know that's a lot. Let's try this one right here. Let's do the same thing. So this one we're already starting in an aldol. We're not starting with an alpha beta unsaturated aldehyde. So that means what I want you to do next is deprotonate. So take it back to when it was an O-. And then I want you to close that carbon-oxygen double bond, and I want you to think, which bond am I going to break? Which of these bonds? I got to break one of them. Which bond am I going to break? Remember, you want to break the molecule in a way, you break it into two pieces. Each piece has an oxygen attached. So think about that. There's only going to be one right way to do this. And we end up with this guy right here and this aldehyde. And this aldehyde is one of our starting material. This second one, the enolate, we're making that by reacting LDA with the corresponding protonated aldehyde. So there's our other one.